Every day, corporations integrate AI agents into their core operations, tasking them with the complex, collaborative work of a full team member. A team environment is inherently messy. It requires navigating asynchronous requests, cross-departmental permissions, and strict organizational hierarchies, where a directive from a department head carries different weight than a query from a contractor. The friction we see in modern enterprise deployments stems from a core architectural limit. Current models are built entirely around the single principal agent problem. In this solitary framework, the AI has a straightforward objective: maximize the utility of the singular prompt directly in front of it. That prompt is treated as the absolute, unquestionable source of truth. Real enterprises are multi-principal environments. An agent serving a team simultaneously receives instructions from a CEO, an engineer, and an HR director, all with intersecting and often conflicting demands. When you drop a single principal AI into a multi-principal workflow, the system fractures. The agent fails to recognize asymmetric authority levels, and it frequently violates strict information boundaries between users. Without a native capacity for role-aware reasoning, an agent cannot safely operate within an organizational hierarchy. To successfully integrate AI into teams, the agent's decision-making framework must be rebuilt. We have to move away from individual utility maximization and optimize for a weighted social objective. Complex prompt engineering provides a temporary patch, but it doesn't resolve why these agents consistently struggle with multi-user dynamics at a foundational level. Look at the first stage of model training, supervised fine-tuning. This phase relies on standardized chat templates to format data. Even when processing multi-user data, the standard interface forces everything through a serialized pipeline. Inputs from distinct individuals are flattened together and assigned to a single anonymous user tag. By compressing the data this way, the model learns a single conditional distribution. It mathematically erases the identities of the participants, stripping away the context of who issued the command. The next training phase, reinforcement learning from human feedback, reinforces this blind spot. Here, the model learns from a scalar reward function. That reward function optimizes for the preferences of an aggregated average user. It conflates the distinct interests of a diverse team into one shared homogeneous metric. As a direct consequence, the AI becomes structurally incapable of distinguishing a high-priority directive from an executive from a casual request from a junior developer. Instead of recognizing organizational rank, the model falls back on its training data patterns, consistently prioritizing whichever user employs the most assertive language. Because there is no native protocol representing individual identities in its architecture, the base model possesses no mechanism to arbitrate conflicting instructions. This training pipeline explains the systematic breakdown observed the moment these models attempt to manage collaborative team channels. Fixing this requires defining a new multi-user environment. We have to treat each user as an independent principal, equipped with their own private context, permissions, and distinct objectives. Instead of optimizing a single utility, the agent must maximize a weighted social objective function across all participants. The variable WI represents the authority weight. It acts as an explicit external priority parameter, giving the agent a definitive hierarchy to reference when user requests directly clash. The agent must also operate under a rule of selective visibility. It acts as a central node, managing information it needs to solve a problem without universally revealing that data to everyone on the team. This is governed by the private context. An HR director has a permission-scoped private context that includes sensitive payroll data. The agent can read this data to execute a task, but the architecture prevents it from leaking the data to unauthorized staff. That restricted data is kept completely separate from the shared context, which holds only the public environment state and approved cross-user summaries. By separating information boundaries and weighing individual utilities, the agent performs a complex aggregation step to find the specific action that maximizes overall social welfare. Integrating these mathematical boundaries into the model provides the foundation for consistent role-aware coordination. To test current model limitations, researchers constructed the Muses bench suite. The first scenario measures multi-user instruction following, feeding models conflicting orders from users of differing ranks. The results are striking. If a CEO orders a halt to a project and an engineer simultaneously commands the agent to continue development, frontier models frequently ignore the CEO entirely and follow the engineer's request. Lacking an encoded authority hierarchy, the models lose all prioritization stability the moment an interaction introduces friction. The second scenario evaluates cross-user access control, positioning the agent as the gatekeeper for an internal payroll database. The data shows that privacy safeguards quickly erode over extended multi-turn interactions. When unauthorized users employ role-playing tactics or repeated requests, the agent eventually falters and discloses the protected data. The third scenario targets asymmetric information gathering through multi-user meeting coordination. This exposes a massive coordination bottleneck. When trying to schedule a time across 4 users, the agent fails to recognize when a specific participant hasn't provided their constraints. Instead of pausing to request the missing schedule, the agent suffers from the hallucination of availability. It assumes a time works for the silent user and finalizes the decision prematurely. The moment coordination requires proactive data gathering and iterative negotiation, success rates plummet across every major model family tested. These controlled stress tests prove that current single-user systems are structurally unable to handle the dynamics of an actual organization. You cannot bypass these failures by writing longer system prompts. A serialized input will always force the model into single principal optimization. The solution requires a native multi-user chat template, preserving distinct identities down to the data format. With these inputs, a dedicated agent core arbitrates conflicts and safely updates the shared context without leaking sensitive information. This sets the stage for the next generation of preference learning. We can train models to maximize social welfare across multiple stakeholders rather than attempting to please a single voice. Establishing native access control and conflict resolution is the only mathematically sound path toward operationally ready enterprise AI. Advancing the frontier of AI now requires building models that natively understand the structural nuances of human organization. By replacing solitary utility with a weighted social objective, we transition the AI from an isolated tool into a reliable, coordinated member of the team.